बिस्मिल्लाहिर्रहमानिर्रहीम। अल्लाहुम्मा सल्लि अला मुहम्मदिन व अला आलि मुहम्मदिन व बारिक वसल्लिम। रब्बि इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली। Assalamu alaikum. I am Dr. Umar Farooq. Here is the title page of your book. Let's first look at the table of contents. This book of yours consists of 8 chapters or units from unit number 9 to 16, comprising of 6 branches of chemistry. Unit number 9 is from physical chemistry, unit number 10 is from inorganic, unit number 11 and 12 both from organic chemistry. Unit 13 itself indicates the branch name. Unit number 14 and 15 both from environmental chemistry, and the last unit is from industrial chemistry. So you are going to study 6 branches of chemistry in this book. So students, unit number 9 is chemical equilibrium. Generally we believe that all chemical reactions go to completion, but in reality most of them never finish. When reactants react to form products, it's technically called the forward reaction. But sometimes there is an opposite reaction that occurs where the products changing into the reactants. We call this a reverse reaction. So on the basis of completion or direction, chemical reactions are of 2 types, irreversible and reversible. Irreversible reactions go to completion and they are unidirectional, which means that they can move in one direction only, that is from left to right. On the other hand, reversible reactions do not go to completion even after years, and they are bidirectional, which implies that they can move in 2 directions, that is from left to right and right to left. We shall now define these reactions in a proper way. Irreversible reactions are those reactions in which reactants are completely converted into products. Consider this general reaction in which A and B react to form products C and D. Such reactions go to completion because reactants are completely consumed and ultimately the reaction stops. These reactions are represented by putting a single arrow between reactants and products. Conversely, reversible reactions are those reactions in which reactants are not completely converted into products and they can go forward and backward. Consider this reaction. A and B react to form products C and D. And then C and D react to form A and B again. The reaction taking place from left to right is called forward reaction, while that proceeding from right to left is the reverse reaction. And when the forward and reverse reaction occur at the same rate, that's called the chemical equilibrium. These reactions are represented by putting a double arrow between reactants and products. Point to ponder. Do not confuse reverse reaction with a reversible reaction. In a reverse reaction, products recombine or react to form reactants, whereas in a reversible reaction, products can recombine or they can react to form reactants. Actually, a reversible reaction comprises of 2 reactions, forward and reverse. This implies that a reverse reaction is a part of a reversible reaction. Let me explain reversible reaction by the following example. Hydrogen gas reacts with iodine vapors to form hydrogen iodide. As hydrogen is colorless gas, but iodine vapors are purple in color, so at initial stage we see purple color in the flask, which fades away as they combine to form hydrogen iodide, which is a colorless gas. This is a combination reaction. At the same time, hydrogen iodide decomposes to form hydrogen and iodine again. And as a result, purple color reappears. This reaction is known as decomposition reaction. The first reaction by definition is the forward reaction, and the second one is the reverse of it. So when both of these reactions are written together as a reversible reaction, they are represented as follows. And this whole story is shown in the following figure. You see, a combination reaction is that reaction in which two or more reactants combine to form single product, whereas a decomposition reaction is opposite of combination, during which a single reactant breaks up into two or more products. Consider another example. Calcium oxide reacts with carbon dioxide to form calcium carbonate. Similarly, if we heat calcium carbonate or limestone, it decomposes to form calcium oxide and carbon dioxide. So first reaction is combination, while second is a decomposition one. Now consider just the decomposition of limestone in an open flask. So I erase the combination reaction. When calcium carbonate is heated in an open flask, calcium oxide remains in the flask, but carbon dioxide escapes out of the flask, and there is no chance of reverse reaction to occur, as carbon dioxide is one of the reactants of reverse reaction. So this is an irreversible reaction and hence goes to completion. When calcium carbonate is heated in a closed flask, then a reversible reaction takes place comprising of both decomposition and combination reactions. Here we have a closed flask in which calcium carbonate is heated. As a result, calcium oxide forms as well as carbon dioxide forms, but cannot escape this time, and there is a chance of reverse reaction to occur. So this is a reversible reaction shown by a double arrow, and hence does not go to completion. Rather, its target is to establish the equilibrium state. So the ultimate goal of every reversible reaction is to attain the state of equilibrium, which is established before the completion of reaction. You have already studied in class 9 physics that equilibrium is of two types, that is static and dynamic. If a body is in the state of rest, it has static equilibrium, and if a body is in the state of uniform motion, it is said to have dynamic equilibrium. When reaction ceases to proceed, it is called static equilibrium. This happens mostly in physical phenomena. For example, a building remains standing rather than falling down because all the forces acting on it are balanced. This is an example of static equilibrium. When reaction does not stop, only the rates of forward and reverse reactions become equal to each other, but take place in opposite directions. This is called dynamic equilibrium state. Dynamic means reaction is still continuing. So at dynamic equilibrium state, rate of forward reaction is equal to the rate of reverse reaction, and concentration of each substance becomes constant. By rate of reaction or speed of reaction, we determine how many number of reactant molecules are being converted into products per unit time. And if the number of molecules of a particular reactant which are being converted into products is equal to the number of its molecules being formed during the same time interval, we say that rate of forward reaction is equal to the rate of reverse reaction. In every reversible reaction, initially the rate of forward reaction is very fast, but after that the rate of reverse reaction increases and the rate of forward reaction decreases. A stage will be reached when the rates of both forward and reverse reactions become equal. This state is called the state of equilibrium. At equilibrium, the reaction does not stop, and both the reactions continue to proceed at equal rates. That's why this state is called state of dynamic equilibrium. It is represented graphically in the following figure, where the reaction rate is plotted against time. As there are two reactions in a reversible reaction, that is forward and reverse, so we plot the graph for each reaction separately. The rate of forward reaction decreases with time, which is shown by this curve. Note that the curve falls down with time, which indicates that the rate of forward reaction decreases with time. On the other hand, rate of reverse reaction increases with time, which is shown by this curve. Again, note that this curve rises up, showing increase in the reaction rate with time. The point where the two curves meet each other represents state of equilibrium. At equilibrium, rates of forward and reverse reaction become equal. Look at the curves again. I hope you understand. Look at the following reaction, and let's draw its reaction rate versus time graph. At initial state, there is no HI, while H2 and I2 are in their maximum amounts and react to form HI. This is known as the forward reaction. Look at its curve. As some HI is formed, it decomposes to form reactants H2 and I2 again. This is called the backward or reverse reaction. Look at the curve. After some time, the equilibrium will set up and concentration of each species, H2, I2 and HI, becomes constant. A common equilibrium phenomenon taking place in atmosphere is the exchange of oxygen and carbon dioxide. We inhale oxygen and exhale carbon dioxide, while plants consume carbon dioxide and release oxygen. This natural balance is responsible for the existence of life on Earth. Macroscopic characteristics of forward and reverse reactions. Macroscopic means visible, जो वाज़े तौर पर नजर आए. In a forward reaction, reactants react to form products, while in a reverse reaction, products react to form reactants. Forward reaction takes place from left to right, whereas a reverse reaction takes place from right to left. At initial stage, the rate of forward reaction is very fast. On the other hand, in the beginning, the rate of reverse reaction is negligible. Forward reaction slows down gradually, but a reverse reaction speeds up gradually. Now, the macroscopic characteristics of dynamic equilibrium. Number 1. An equilibrium is achievable only in a closed system. 2. At equilibrium state, the reaction does not stop. Forward and reverse reactions keep on taking place at the same rate but in opposite direction. 3. At equilibrium state, the amount or concentration of reactants and products become constant, that is, they do not change. Even physical properties like color, density, etc. remain the same. And number 4, an equilibrium state is attainable from either way, that is, starting from reactants or from products. And number 5 is, an equilibrium state can be disturbed and again achieved under the given conditions of concentration, pressure and temperature. I hope you understand. If you have any questions, please do write in the comments below. Thank you.